10 to the power 6 Newton mm. Okay, so our first step is over of calculating the maximum value of bending moment. Right, now what is our second step? Second step is we have to calculate from the cross section the value of y and value of I. Right, so y, to locate y I have to locate CG. CG is obtained by intersection of diagonals. So intersection of diagonals will give us the CG. So from CG neutral axis will pass. So neutral axis is passing from the CG. Okay, so we can see that this is the neutral axis. I can write down over here NA. Okay, now what will be y? Distance of extreme fiber with respect to neutral axis, that is nothing but d by 2. So we can write down y, that is equal to d by 2, that is equal to 300 mm. Okay, and what will be I? I is nothing but moment of inertia for rectangular section. What is our standard formula? BD cube by 12. So BD cube by 12, we can get the answer of BD cube by 12 as 1.8 into 10 to the power 5 mm to the power 4. Okay, so we have got the value of all these three things. Now what we are going to do? We are going to put it in our standard formula. What is our equation? How do we remember? My fire, right? That is m upon I, that is equal to FB upon Y, that is equal to E upon R. They have not given E, they have not given R, so we are going to use this both. Alright, so now FB, that is equal to M Y upon I. Okay, what is the value of FB they have given? 10 Newton per mm square. That is equal to M we have calculated as 4.5 W into 10 to the power 6, right, into Y we have calculated as 300. Okay, and we have got the value of I as 1.8 into 10 to the power 5. So when you solve this equation, you will get the value of W, and W is nothing but 40 kilonewton per meter. Okay, this is the answer, right? That is 40 kilonewtons per meter. Now we go to the third problem. It is a very important problem in which you have to calculate the total amount of load. Right, now how do we basically calculate a load? When we have, if I take a very simple example, that you have got a wall, right? The wall is having no openings, that is, there is no door, no windows. Okay, we have got a 3 meter height, wall, and its thickness is 30 centimeters. Okay, now if I want to find out the load given by this particular wall on the floor, how can we calculate? Right, so I will require the density of the material. What material is used? Material used for making a wall, that is nothing but the cement concrete. So we'll require that material. Then I have to calculate the wall is having same thickness and it is having same height throughout. That means it will transfer a uniformly distributed load. So what I will do? Area multiplied by the density. Okay, now what will be the area? So area will be nothing but height and the thickness, and I'm going to find out per unit length, right? So I'll get W kilonewton per meter. So this concept we are going to use in our next problem. That is, what is the problem? First read that particular problem. So the problem is that we have got cast iron water pipe, right? Cast iron water pipe, and it is 400 mm inside diameter and 450 mm outside diameter. It is supported at 2 points 6 meters apart. Find the maximum stress in the metal when the pipe is running full. The density of the metal is 7 grams per centimeter cube and that of water is 10 kilonewton per meter cube, right? That means we have got a cast iron water pipe. So the material is cast iron. So I will require the density of the cast iron, right? Now they have told that it is carrying water and the water is running full, right? So we have to consider the density of water also. So first of all, I will try to draw the diagram, right? Now what they have told you, it is a cast iron water pipe. So water pipe, so what will be the cross section of the water pipe? It will be a circle because they have given you the inside diameter and the outside diameter, right? So we can show that it is having a circular cross section. Circular cross section is given and the internal diameter is 400 mm. So we can write down over here that the internal diameter, that is equal to 400 mm. Okay, and external diameter that is equal to 450 mm, right? So we can show external diameter with another cross section. Okay, so this is external diameter, that is 450, and this is internal, that is 400, right? Now what they have told, that it is running full with water. So we can show that inside it is subjected to a load of water, right? So water is there. Then they have told that it is supported at two ends. So this is a pipe, right? And it is supported at both ends for a distance of 6 meters, right? So this is our diagram. Now we have to first see, as the both ends are supported, that means it is which type of a beam? It is a simply supported beam, right? So we can show it is a simply supported beam. What is the span? Span is 6 meters, so we can show 6 meters. And as the water is running throughout the length of the pipeline, it will distribute a uniformly distributed load. Okay, so we can show that over here you will have a uniformly distributed load of intensity W kilonewtons per meter. Now I have to calculate this particular W, right? So the first step will be to calculate uniformly distributed load, right? Now how to calculate this uniformly distributed load? So two types of loads will be coming. First is self weight of pipe, okay, and the second is weight due to flow of water. Okay, so now first of all we will calculate the self weight of the pipe, right? Now to calculate the self weight of the pipe, we can say that W1, that is equal to nothing. We are finding out W1 per unit length. You are finding out W1 per unit length. Okay, so W1 per unit length, so L will be 1 meter we are considering, so that is nothing but area of pipe multiplied by density of pipe. Okay, now what is area of pipe? So area of pipe, that will be equal to pi by 4 into external diameter square minus internal diameter square. So pi by 4 into external diameter is 450, so I will write down in terms of meter because I want to find out the load in terms of kilonewton per meter. Okay, so I am writing down in terms of meter, minus 0.4 square. Okay, so we get the answer is pi by 4 into that is 0.0425 mm square. Okay. Now important part is density of the metal. If we see what they have given the density of the metal, the density of the metal is 7 grams per centimeter cube, right? And I want it in terms of kilonewton per meter cube. So density of metal they have given us as 7 grams per centimeter cube. Maximum mistake the students make is in conversion, right? So I'll show you the conversion. First is I want to convert the gram in terms of kilonewtons. So we know that 1 kg that is equal to how much grams? 1000 grams. Okay, so 7 grams that is how much kg? So 7 upon 1000 that will be kg. Okay, then we know that 1 kg that is equal to 10 newtons, right? 1 kg that is equal to 10 newtons. So 7 upon 1000 kg is equal to how much newtons? So we get it as 7 upon 1000 into 10 newtons, right? Now I want to convert it in terms of kilonewton. So we know that 1 kilonewton is equal to 10 to the power 3 newtons. So 7 upon 100 newtons is equal to how many kilonewtons? So 7 upon 100 upon 10 to the power 3, that is kilonewtons. Okay, now we know that centimeter cube, so we know the relationship between centimeter and meter. 1 meter is equal to 100 centimeters. So directly I can write down as 7 upon 100 into 10 to the power 3 is equal to into 10 to the power 2 into 3. 10 to the power 2 matlab 1 meter is equal to 100 centimeters. Okay, and as it is cube, so we are multiplying by cube. So we get 70 kilonewton per meter cube, right? So this is density of metal. So now I can find out my W1. So W1 that is equal to 0.0425 multiplied by 70 kilonewton per meter cube, and this is meter square. So this will cancel out, this will cancel out, you will get into 70, you get it as 2.975 kilonewton per meter. Okay, this we have calculated W1. Now we will calculate W2, right? So what is W2? W2 is nothing but the flow of pipe. Now what is the main difference? In this I will take the area, but area of internal diameter of pipe. Why internal diameter of the pipe? Because water is flowing inside, right? So we have to take that multiplied by the density of water. So pi by 4 into 0.4 square multiplied by what they have given density of water. Density of water they have given you as 10 kilonewton per meter cube, right? So multiply by 10 kilonewton per meter cube. So this meter square will get cancelled out. So you get it as pi by 4 into 0.4 square multiplied by 10. So you get it as 1.25 kilonewton per meter. Okay, so what is our UDL? Final answer for uniformly distributed load, W. So W, that is equal to W1 plus W2. Okay, so that is equal to 2.975 plus 1.25, that gives you 4.231 kilonewton per meter. Okay, so we have completed our first step, that is we have calculated W. Right, now after calculating the W, I can find out the maximum bending moment. It is which type of a beam? It is a simply supported beam subjected to a UDL. So it will be WL square by 8. Right, so now I can show my diagram that we have got a simply supported beam having a uniformly distributed load of intensity 4.231 kilonewton per meter for a span of 6 meters. Okay, for a span of 6 meters. So we can say that the maximum bending moment will be equal to M, and that is nothing but WL square by 8. So that is equal to 4.231 into 6 square divided by 8. So that gives you 19.042 kilonewton meters. That is 19.042 into 10 to the power 3 newtons into 10 to the power 3 mm, Newton mm. Okay, then second is what they have told us to find out. They have told us to find out the maximum stress, right? So what is our equation for maximum stress? Our standard equation is my far air. Okay, so they have given this, so we'll use this. We have calculated M. Now we'll calculate I. So what is I? I is nothing but moment of inertia. And what is moment of inertia?